You still remember this transfer function or this block diagram is a controller and your plant CP. Alright, this is a first order system because in order to change your plant, alright, you only use your controller. Alright, you can alter your controller transfer function to control your plant, some sort. If you have a filter, extra filter over here, then instead of just a controller, you can also have another filter over here to control your plant, to change the deviation of your plant. So the more controllers you have, the more degree you have, or the more block diagrams you have, the higher degrees that you are. Alright, so therefore we introduce instead of the filter, we still deals with the controller. So therefore I change the controller to a PID controller. So this PID controller is somewhat like a second order so-called system, right? 2 degree of freedom, 2 degree of freedom of a system to control your plant. So how does this work is that we have a proportional controller over here, you have an integral controller and a differentiate derivative controller over here. So what it do is that you have a reference signal, you go through all this stuff, alright, and the plant output and feedback to you. Alright, so you take the reference signal minus away the output equals to your error, right? So this error will go through your proportional I and D. So your controller is somewhat to do things with in terms of the error itself. So how does this do things with that? The proportional controller is simply multiplied by Ki. Alright, so it's just simply proportional, meaning if the error is 5 and you expect your output to be 1, you just times 0.5. Times 0.1. So therefore 5 times 0.1 is 1. Alright, so this is the method to use the proportional controller to this extent. So you no need to activate I and D. Okay, but things are not that easy as we see. So let's continue first. Actually this should be Kp. Alright, this is the proportional, so it's Kp. Alright, then we have a Ki for the integral, alright, and we have a 1 over s. Alright, we say that 1 over s is integration, while Kds, this one is differentiation. So why do I say 1 over s and s? This one is integration, this one is differentiation. Why? For example, we have an error over here, and then we multiply by 1 over s is equals to output y over s. Alright, so if you were to bring this s over to this side, what we have is e over s is equals to sys, which is also equals to dy dt. Alright, so from this case onwards, what can you see is that e over s at this particular point, or et, is dy dt, which is over here. Okay, if you go through 1 over s, you'll become yt, which is this one. Alright, so your et is over here. If you were to multiply by 1 over s, you'll get your yt. So that's just the meaning of that. You can work the other way. Alright, since you have et equals to dy dt, so if you Laplace, you have es is equals to sys. Same thing. So you just bring this s over here, you have e over s is equals to ys. So your es times 1 over s is equals to your ys. So we know that just now from this one, we know that your es or et is equals to dy dt, which is here. So once you go through the 1 over s, you become integrated, and therefore it's over here. So I hope that this is pretty clear and pretty in-depth to you before we go on to other stuffs. And since integration you're dealing with 1 over s, then differentiation is simply s. You can just remember, or you can just try it out. Alright, that's the same example. But just take note that integration is 1 over s and differentiation is times s. So far so good. For a pure P controller or proportional controller, there is some sort of a problems. Or what is the problem is that the behavior of it is that when you input a small proportional gain, alright, you have something like this. Alright, and eventually it becomes stable. Alright. But however, your controller performance will be slow, right? Because your gain is small, right? Your gain is small, this means that you'll be slow. If your gain is big, then you'll be fast. So normally we want things to be fast, and therefore we decided to increase the gain. So when we increase the gain, when Kp is increased, alright, the overshoot in the signal will be present. Therefore this thing spikes. Alright. Therefore for high gain, alright, it is not easy to achieve your low steady state error. Steady state error means that you're going to talk about is that when you take a reference signal, you minus away your output, you have error. Correct? So if you input 1 volt, alright, and your proportional gain is about 2 times 2, alright, your output will be maybe because of going through the plant, it may be 1.5 volt. Alright, so when you feedback over here, so 1 volt minus 1.5 volt, you have an error of minus 0.5 volt. Alright, and therefore from this you can see that your steady state error is minus 0.5. Maybe we should draw over here, minus 0.5. Alright, somewhat still okay. Alright, the error is that you need to minus away your 0.5 volt because you decided, because you want your output to be just 1 volt, but you exceeded as 1.5 volt. Alright, so this is that's why it tells you to minus 0.5 volt in such a case. Then if you do proportional gain times 20, then this thing will gonna go about 35 volts now. Alright, and therefore if you have to feedback, alright, 1 volt minus 35 now is minus 34, which is a huge, because this is a huge gain, you'll create a huge error. Alright, so it's minus 34 error, which is pretty large. Alright, therefore this is something of a steady state error, and that is all it is. Alright, and therefore for proportional gain or proportional controller, you can only allow small proportional gain, and that's all. Alright, in order to achieve low steady state. If you were to go high, then you're gonna haywire. Alright, so I shall just take down. Alright, so for small gain, you have a slow performance, but if it's a big gain, it's bad because performance is fast, you're unstable, and therefore a big steady state error. Alright, and just to show you that the big steady state error in terms of this graph is this thing. Alright, for a low, maybe this, I should change a different color. Maybe for a low gain, your steady state error somewhat goes to here. Alright, but for a high gain, as you can see, your steady state response go somewhat higher. Alright, you're having such of a big chunk of difference, and as your gain increases more large, you have more larger of a steady state error. Alright, because you only want your response to be here, but your error is so big. Alright, so instead of just the proportional control, we will use proportional integral. Alright, PI in this case. And what will we see? We see that your steady state error over here is actually 0 compared to the difference over here. Alright, there is such a big difference of a steady state error. Okay, and therefore this steady state error over here is simply 0. So for a PI controller, your steady state is actually 0. But because you're talking about integration, meaning if you have some curve over here, you're gonna integrate all this part. Alright, you may have some spikes, maybe sometimes it's go like this, and maybe the rest continues. So this spike actually over here, because if you were to just take a look, the integral term is responding to accumulate errors from the past. So if you were to accumulate this particular area over here, this particular area that is pretty large pass, alright, you're gonna have such of a big spike over here, right? And therefore this spike will actually cause a deviation in other directions. I don't know where is the direction, but yeah. And also you require more time, alright, more time to settle down. So what do I mean by more time to settle down? Because if you want to remove this, because you want your whole steady state to be 0, so your whole integration over here must, when you sum it all together, must be 0 also. So when you receive such of a big chunk over here, you're gonna have another big chunk over here to control. Alright, eventually this thing will die down to 0. So when you sum it up all together and minus each other, this equivalent is equals to 0, and therefore steady state error is 0. But however, it takes time to do this and alter, to control this until it's 0. So therefore it requires a certain settling time. Okay, and if you were to increase the settling time, because your settling time is so slow, you want to lower it such that you can do things faster, because you want a response to be fast, right? But so therefore you increase your gain, and if you were to increase your gain, Alright, this means that you're going to create this spike over here, things like that. So these are the things that you may need to consider. So somewhat the PI controller is to deal with the steady state error, so ensuring that it's going towards 0. You have a good transient response because it's somewhat not very much oscillatory. You'll just somewhat die down compared to your this part over here. It is very oscillatory, or it's very rampant. Comparatively over here, this is somewhat smoother for the transient part. Alright, and it requires a high settling time to become steady because it takes time to accumulate all this, ensuring everything is fine. And the overshoot may occur due to the past accumulated data, which is this one over here. Alright, and therefore this PI controller somewhat reflects the properties of an integral controller. Alright, so because if the proportional controller is simply just to control the gain itself. So if you were to multiply with an integral controller, somewhat you're talking about the PI controller is somewhat simply dealing with only the integral controller to some meaning. Alright, so this somewhat descriptions can also be applied to your integral controller. Alright, purely integral controller. Alright, but before I go to the PD controller, I'll just say that for the pure proportional controller, big transient response also for high gain. Alright, because we have just discussed for proportional gain, from proportional controller is very oscillatory, alright, comparatively to your integral controller or PI controller. Is at least the oscillation is very minimum. Okay, so now let's go to PD. Sorry. So what is PD different from PI? Alright, PD is talking about proportional and the derivations of stuff. Alright, so we ignore the I first. Alright, so the derivative term slows the rate of change of the controller output. Alright, because if you have a high rate of change, for example this slope or this slope over here, if I were to draw the curve like this, alright, your data actually your responses could actually be very violent. Alright, so we want our changes to be as minimum as possible. The changes aren't this big, so the derivations or maybe dy dt is equals to 0, and therefore it's somewhat pretty safe. Alright, so the derivative part is actually to deal with the changing trend. Alright, and eventually slowly control the trend from like this to maybe like this, and then like this, and then like this. So you somewhat change the trend to somewhat 0, so that there is no changes, or the rate of change is simply 0, and therefore putting your system to be stable. Alright, and is used to reduce the magnitude of the overshoot. Alright, so normally the overshoot just now is like this, so with your derivation you actually control. Alright, because the overshoot itself is talking about the changes in the derivative. Alright, there's a slope over here, so if you were to minimize this derivative, alright, all the way until it's 0, this means that you're somewhat allowing your overshoot to be somewhat pretty safe due to the derivation. Alright, however, because your error is mixed, because if you were to all the way go back, alright, it's over here, your error itself is feedback from some disturbance also, if you still remember. So the disturbance may actually add up to your error and contributes to your overall system. And if the overall system is mixed with your controller, and your controller, because your error itself is together with the noises already, the disturbances, and therefore if your error controls this overshoot, we shouldn't be here, but yeah, here, PD controller, and if you were to control the overshoot over here such that it's pretty smooth, alright, you can somewhat also amplify the noise, alright, because you're allowing the noise to mix together with your reference signal. Alright, I think you get what I mean, because the noise is embedded in your error now, and then if you were to adjust your error, you're going to adjust your noise all together, so therefore your noise and error together, and you make your noise and error to be somewhat the same of the magnitude or whatsoever, such that you are amplifying your noise, so your reference signal may not be exactly correct already, and this is the thing of it. So this differentiation part is highly sensitive to noise in the error term, right? And can become unstable, alright. And also your PD controller can decrease the settling time, so you take lesser time to actually settle down, because you're just straight away goes to your whatever your gain is, and that's it. Alright. And however, to control this steady state error, because there is also steady state error, if you just take a look. Alright. Because there's a difference. If you were to compare to the PI controller, do you see all of the signals over here all becomes like this. They're all going to the same output response, alright, of 1. However, the steady state error means that when you reach a certain, so when you want your output to be 0.7, for example, when you input a certain errors and eventually those stuff starts to go to 1 and maybe higher than 1, things like that. So there will be an error between what you input of your gain and the responses, what you desire your output to be and the responses it is, something like that. Alright. And therefore we reduce the overshoot and the settling time, and so however it's sensitive to noise, and as your steady state error is high, alright, you can actually increase your high gain or your KD, or in other words the constant that we have seen just now, this KD over here. You can increase this KD, but however you're gonna make your system more sensitive to noise. Alright, so there's some control in terms of trying to find the optimum way of doing your stuff. Alright, and therefore as you can see, for let's ignore the proportional controller because it's just some constants. Let's talk about PI and PD. Alright, is that PI has a steady state error, has no steady state error, meaning it's 0. Alright, meaning if you have a low gain with something like this and a high gain, alright, normally steady state error means that you will not, or in other words, this is your desired output. Alright, but however, when you increase your high gain, the steady state is actually over here. So your error between your response and the output that you want is such of a high error, and therefore this is not good. Alright, but however for the PI controller, you're actually allowing your high gain to go to 0, or not 0 but rather than go to your whatever desired output. Alright, but however you can't deal with the overshoot. Alright, the setback is the overshoot. So on the other hand, your PD controller is to reduce your overshoot. So therefore the PD starts to help out with the PI. Alright. And as for the PI, this is good stuff is that its steady state error is 0, and therefore as for the PD, the steady state error is high, and therefore your PI can help your PD. Okay? And therefore for the PI and the PD is normally most suitable for really high gains. Alright, for high gains. If you're talking about just, I would say that PI and PD merge together. Alright, you can have suitable for high gain. As for proportional only, small gain is good, it's just right already, but performance is slow lah. So if you want fast performance and high gain, because high gain will initiate fast performance, and therefore you require a PI and a PD controller. If you merge them together, you'll have a PID. Alright, and therefore as you input your gain, your small gain is somewhat over here, quite safe. If you were to input larger gain, alright, somewhat over here. So it's somewhat being controlled in such a good manner, as you can see. Alright, and just to let you know that reduced bandwidth means that you're going to slow down your feedback system. Alright, so normally we want high bandwidth so that you can increase your feedback system, or the speed is increased. So if you want the speed to increase, you want to input a high gain. So high gain, high band, but high bandwidth, sorry. Alright, but it's very unstable, and therefore you will require your integral controller to bring your error to 0 steady state. Alright, that's very important. In the next video, I'll just briefly give you a few understandings about the P, I, and D, about individually how their graph trend will behave. And then we will talk about the graph trend of your PID controller. And I shall see you there.